There is a big problem when it comes to satellites in low Earth orbit. Although you might think of it as space, the atmosphere continues upwards while its density decays exponentially. This means the spacecraft experiences a very small drag force that over time causes it to deorbit. Satellites combat this by carrying fuel to boost orbit periodically. The International Space Station has to do it about once a month. The trouble with that is getting fuel into orbit is very expensive. It was estimated to cost $1.8 billion to transport fuel up to the International Space Station over the course of 9 years. Our CubeSat will contain what's known as an electrodynamic tether. Shown here is one that NASA tested on board the Space Shuttle. This is a long, powered wire connected to the satellite, and through its interactions with the Earth's magnetic field, we can raise and lower a satellite's orbit. The tether uses no fuel, and through this will lead to dramatic savings in fuel costs. When a powered wire moves through a magnetic field, a force is produced. Our CubeSat will have a long wire attached to it, and while in orbit, the wire will cut through the Earth's magnetic field lines. By passing a current along the cable, our satellite will produce a force that can be used to increase the satellite's orbit, as shown here, by operating it at key points in its orbit. The only fuel required for this is electricity, which will be supplied from the CubeSat solar panels. The tether can also be used in the opposite way. By not powering the cable, the satellite instead gathers power, decreasing the satellite's orbit. While the Earth's magnetic field may be weak, so is the force due to atmospheric drag. In fact, a force of only 20 micronewtons was required to combat the orbit of a satellite launched by the ESA from degrading. The satellite had much more atmospheric drag on it due to being larger. The primary objective of our mission is to see if the tether can affect the orbit of our CubeSat, and if we can reliably predict how much it can change. If we can do this, our goal will then be to prove that the effectiveness of the tether can scale up, and can be used on other large commercial satellites in place of propellant-based propulsion. The tether can be used to both raise and lower a satellite's orbit. There are commercial opportunities for both functionalities. A satellite's lifespan is limited by the amount of fuel it brings. If a satellite has a tether on board, then its fuel comes from an unending supply, the Sun, and once the tether is deployed, there are no moving parts to fail. With the electrodynamic tether, a satellite's lifetime can be dramatically extended. That means there is a commercial opportunity to build and sell these tethers, if this CubeSat mission proves them to be effective. There are two main sources of data from our spacecraft. One will be the amount of power put into or extracted from a tether. This will be measured via an onboard computer. The other main source will be the orbital positioning data, via an onboard GPS unit. For our control, we will use either known models for orbital decay, or if our CubeSat is launched in conjunction with other CubeSats, then we can use those as our control. In summary, the electromagnetic tether solves a problem using technology in a novel manner. It provides an opportunity to test this concept on a small-scale CubeSat where it has not been successfully tested in the past.